Hello, good evening, everyone.
Good evening, sir.
Sir, good evening.
Yeah. So I think this is where we are. This week we are going to have week five, and then next week we will be having revision sessions, right? So yeah, I don't know how many of you have watched the lectures for week five. Let us see. Let us start. I'll give you the overall idea about week five. Maybe we'll try to complete today, like whatever the broader level ideas are there. It's okay. First of all, take a poll. Like, how many of you have? You can raise your hands. How many of you have watched lectures? All lectures. All lectures.
Sir, not all.
Okay. So how many? Like, maybe at least
Not
half of it. Half of the lectures.
half of lectures we have seen.
Yes, sir.
Half of you have seen, right?
Yeah,
Okay.
diagonalization is difficult.
Yes, sir. I had not understand that 5.4 lecture.
Okay. You didn't understand 5.4
No.
lecture. Okay, fine. So it's kind of the similar thing we have done, right? But little bit different because the complex matrices are there. Otherwise, it's kind of a similar process. But let us try to understand it better, right? Okay.
And sir, how to find the eigenvectors of 3 into 3 matrix of complex matrices? That also.
It will be the same thing, right? Same process what you do for 2 cross 2. What you do, or in a real, or maybe 3 cross 3 in real scenario, what you do?
Sir, but it is making a 3 power equations. So how
But
to solve that?
how to solve is the thing, right? So mostly, see, in a quizzes and all, we'll not ask you to solve those. But can you just give me a minute? I'll just.
Okay.
Okay. Yeah. So yeah. Fine. So I think, see, it is how to find the eigenvalues of 3 cross 3 matrix. Maybe we'll see that. Mostly we'll be dealing with 2 cross 2 only. But let us try to understand the concept first, and then we'll see how to solve the problems, right?
Okay, sir.
Yeah. Okay. So the part which you don't understand, what I feel is the how to find out the what is the diagonalization of the matrices. Right? Okay, done. Maybe I'll just start with the simple things
One,
first.
one, one more request, sir.
Yeah.
So we are doing the standard method. Suppose we are finding the eigenvalue, the standard procedure is there. But
Yes.
sometimes sir also does the by the eyeballing the this is the eigenvalue. That trick, that is the method of, I do not understand how they do that eigenvalue is this.
No, I don't understand what like he has directly written something.
Yeah, yeah.
So he
Sometimes
might have solved it already. It's not
I
like
think the professor had already calculated it.
yeah, that's what. It's not like
the
there is a
okay.
trick or something. He's not
Let us
because
let us go by the standard method. It is better.
Sir, I think there is a one trick that if the matrix is lower upper triangular matrix, then the diagonal elements are
that everyone knows, right? Like
Yes, sir.
yes,
for
yes.
upper triangular, lower
Yeah.
triangular, and the
No.
diagonal
Yeah.
matrices,
Yeah. Yeah. Hmm.
the because it's very easy, right? Because the trace of the matrix is equal to the sum of the eigenvalues, and the determinant will be equal to uh, product of the eigenvalues. So if you see that these two, if you use these two properties, I think from there you can so for upper triangular or lower triangular matrices and diagonal matrices, whatever the values along the diagonal are there, they are the eigenvalues, right? I think all of us, I think, know about that, I believe. Okay, let us try to understand. Okay,
Okay.
maybe let's
Okay. Okay.
start
Okay.
with
Okay.
yeah. Along
Okay.
with that,
Okay.
maybe we'll try to see what is the things, right? Okay, first place, what is the difference between the vectors which are like which are the real vectors and the complex vectors? uh, that is the, yeah, basically we'll use the complex numbers in the vectors, right? That is the one part. One more thing which we have to understand is, there is in real values, right? For real values we don't have the conjugate, but for complex values we have the conjugate. So what is the conjugate? uh, Conjugate of the vector is, let us say you have a vector a, which is, I'll say the complex vector, which is, let's say, 1 and I. What is its uh, conjugate? There is, so conjugate is basically you will have to uh, use the, so wherever the complex numbers are there, we'll have to change the sign of the complex values, right?
Yeah.
And that will
Yes,
give
sir.
me the conjugate. So this is called as the conjugate of, or maybe sometimes they'll call it as complex conjugate, right? Complex conjugate of A, right? So let us say B is equal to 2 plus I and 3 minus I. So what will be the complex conjugate? And it is shown by the bar over the vector. So it will be 2 minus I and
2
3
minus
plus I.
I, 3 plus I.
So that is your complex conjugate. So you understand, right? So how to find out the complex conjugate of any maybe complex number also, will have to change the sign. Is that fine? Okay.
Yes, sir.
In real scenarios, we say the two vectors A and B are orthogonal to each other. And if the A and B are orthogonal to each other, then in that case what we write is the dot product between these two vectors equal to 0, or in vector form
A transpose.
A transpose B equal to 0. That is what we write generally, right? In complex case, this will not be true, right? Okay. A, if it is, let's say it contains some values, right? In that case, what is this mean by? So A and B, let's say you have some elements into those vectors. We'll write them as A1, maybe let's say A1 dot B1 plus A2 dot B2 plus A3 dot B3 equal to, and like that up to AN dot Bn equal to 0. What is this? So basically A is a vector where the values are A1, A2 to An, and similarly B is a vector where the values are B1, B2 up to Bn, right? And in real scenario we say that A, the dot product between these two vectors equal to 0. That means this, right? Is that correct? I hope this is fine.
Yes, sir.
For real case it is the it is the case, but in complex case it will not be the same case. It will be, let's say, a, let's say I'll take two different vectors, let's say z and w, and the dot product between z and w is not equal to z1. So okay, okay, I'll tell you what is z and z1, z and w. So suppose your uh, your z is like this. So z equal to, say, it's a vector which contains values z1, z2 up to zn, and w is a vector where the values are w1, w2 up to wn. Fine. So if these are the let's say these two vectors are there, then the dot product between these two vectors will not be equal to z1 dot w1 uh, plus z2 dot, what is this dot, you know, right? This,
Dot
the dot
product.
product between the, so when actually it's like z1 into w1 kind of like that, right? Up to zn dot wn equal to 0, right? If z and w are orthogonal. But in this case, if these values are uh, the complex values, right? In that case it will be equal to z1 dot w1, z2 dot w2, like that. And then it or maybe I can say, so it's okay if they we'll see about the orthogonality later. the dot product between these two complex vectors will be written by this. So what will be the dot product between W and Z? W dot Z will be W1 conjugate
The conjugate
Z1,
Z1 plus
W2
W2
conjugate
conjugate Z2.
Z2, and like that Wn conjugate Zn. So can you say that Z dot W is equal to W dot Z? Will this property hold true or not? The dot product between Z and W and the dot product between W and Z, will they be same or no? By looking at above equation, what do you say?
No, no,
They
it
are
is not
not.
the same.
Yeah,
Not the same.
but in the real case, these two are same, right? In the if the numbers are real, then we will try to understand through numbers. Let's say you had the two vectors a equal to, let's say, 1 2 and b equals to 3 4. What is the dot product between these two? A dot b will be so either it will be a transpose b, right, or uh, b transpose a. Okay, and let us try to see there whether these two are same. So what will be this value? 3 plus
8.
8,
8.
which is, maybe I'll say that 11, right, equal to
11.
11. It
11,
is
right?
correct. It is correct.
Right. So that means if I a dot b, let's say it, if I say that a transpose b and b transpose a, they both are
Same.
same, right, in the real case. But in complex case, let us take example. So let's say Z is 1i and W is, let's say, 2 plus I and 3 minus I. Okay, so these two values are there. What is the what is Z dot W? Basically we said that it's like
Z
Z conjugate
conjugate.
transpose W. So what is the conjugate of Z?
1 minus I.
1
1
minus I,
minus
and
I.
this will be the transpose, and here it is
2
2
plus.
plus I and 3 minus I. So if I just multiply this, it will be 2 plus I minus I into 3 minus I, right? So that means it should be equal to 2 plus I minus 3I plus I square, which is, so I square will be minus 1, right?
Minus 1.
So I square is equals to minus 1, and that is the definition of a complex number. So yeah, so 2 minus I is 1 minus 2I. So the Z dot W is equals to 1 minus 2I. Let us try to see what is W dot Z is. So W dot Z will be W conjugate transpose Z, right? So what is the conjugate of W? It is 2 minus I and
2 minus I, 3 plus.
plus I, and here it is 1 minus I, or okay, plus I, right? Because Z is 1 and I, right? So yeah. Okay, so what will be the dot product? So it is 2 minus I plus I times 3 plus I. So it is 2 minus I plus 3I minus I square. So minus I square will be equal to minus 1.
Minus
That means
1.
plus, that will actually give me plus 1. So it will be 3 plus 2I, right? So you will
Yes.
just see that W, this is W dot Z and this is Z dot W. So Z dot W is not equal to W dot Z. Is that fine? Okay.
Yes.
Yes, sir.
No issues till now, right? Okay.
No.
Sir, here is plus now. 3I plus I square. Then it will become minus 1.
What is it?
Sir, in last second line, 2
Huh.
minus I plus 3I plus I square now.
Okay, plus I square. Okay. That is okay. Plus I square, right? Huh. Okay. Still it will not be the same, right? That
Sir,
is correct.
1 plus 2I now.
And here it is 1 minus 2I, right?
Yes, sir. So
So
we can say that z dot w is equal to uh, w dot z conjugate.
no, no, no. We cannot say, right? Okay, that will not be true. Maybe it is coming here. Let us see. I don't know. The values are coming like that only, but it is uh, not. I don't think it is like every time we will get the same thing, right? You can try with some other numbers. Here, if I done correct calculations, right? 2 plus I minus 3I plus I square. So yeah, that is correct, right? Uh, Correct, correct. The calculations are correct, but the thing is, you cannot say that z dot w will be equal to, I think, the conjugate of that, right? Or you can say
No, no, it is not possible. Anything can come, na?
that is what. See, so maybe we'll take one more example. We'll try to see that whether it will be correct or not. Let us say I'll take one more example with, let's say, z equals to uh, and w equals to. Okay, fine. So in this case, what will be z dot w? It is conjugate transpose, so it is minus I, and here it is 2 plus I and I, right? So if I do the calculation, what it will be? Minus I into 2 plus I and minus I square. Is that correct?
Yes.
Okay.
Yes, sir.
Minus 2I minus I square. So it will be minus 2I and
Plus
minus
2.
2I square. So that 2I square will be
Plus
plus 2.
2.
So basically it is 2 minus 2I. And if I do w dot z, in that case, w conjugate transpose is
2 minus I minus I.
2 minus I, and here it is I. Right. In this case, what will happen? Let's see, 2 minus
2
I and uh,
minus I square.
so this will be
4.
2I square I square. So it will be 2I plus 2, right? Yeah, I think that's what you're saying, right? Is that correct?
Yeah,
Yes, sir.
this is also like
Yeah, I think then I think, but I don't know whether it is correct or not. But if we look at it, it seems like maybe I'll cross check it later on. I
So
haven't seen
it's
that.
there in one of the activity question also, the
The-
property.
yeah, so maybe this is a property. So that w dot z will be what? Z dot w conjugate. Huh?
Yes, sir.
Yeah, sir. In the
Yeah,
lectures
I think
also.
you have to prove that. Yeah, that's okay. Yeah, maybe it's correct.
yeah. This is the properties. Okay.
Yeah,
This
okay.
is the property.
Yeah, fine. So that's okay. You can anyway you can verify at any point of time, right? So no issues with that. Fine. Okay, so let us move towards. So I think these are the basic things we have to. One more basic thing is if you have a vector z, which is, let's say, any complex vector, suppose I minus I, what is the length of z? In the real scenario, that will be what? Z dot z, right? Root of z dot z, right?
Yeah.
Dot product between the it's like the same vector, right? And you will take the square root, that will be your length of any vector. But in case of complex number, will that be the correct answer?
No, no.
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 And why it is that? Because it will give me value 0 every time, right? The product, if I use the same product, then it will not be the same. Again, why it is not there? Because we know that dot product in complex scenarios, how will you do that? We'll have to take a conjugate, right?
Conjugate.
Conjugate of this, and this will be this will give me the length of a vector uh, in complex uh, uh, right. So when we use the complex vector space, is that correct? Okay.
Yes.
So I think these are the basic things which we need to understand the further discussion, right? So okay, so let us discuss more about it. Fine. So let us see.
So what is the notation for the complex vector space? Do you
Yeah,
use
Cn, C,
C?
C. Yeah, this is like Cn. Yeah, we generally we use R for real, right? And we
Yeah.
just try to use the one more extra line to denote that capital R.
Okay,
Similarly for
okay, okay.
C, I'm just using that
Okay,
extra
okay.
line. That's it, right? So
Okay.
this is for real vector space, and this is complex vector space. Okay.
Okay. Okay.
Yeah. So now there is like a very important matrix in case of complex numbers. We'll try to see the analogy between the real numbers and the complex numbers, or maybe real vector space and the complex vector space. In real scenario, we have a transpose, right? Uh, so when we say A transpose equal to A or A equal to A transpose, these matrices are called as what? The matrix A is, or vector, sorry, not matrix,
Symmetric.
or matrix also. Okay, matrix A will be symmetric matrix. So similarly, in complex case, uh, if the complex conjugate, uh, right? So if you're sorry, if A equal to transpose of complex conjugate, or the conjugate of A transpose, if that is equal, then we this is kind of
Hermitian.
a symmetric matrix, but we call it as a Hermitian matrix, right? So Hermitian matrix, and generally the complex conjugate transpose is denoted by a star or sometimes H. Okay, so these are the notation for uh, complex conjugate transpose of a matrix. Okay, if A equal to A conjugate transpose or A transpose conjugate, so in this case A equal to, we can write like that also. So both are equal, right? So A transpose conjugate or A complex sorry, A conjugate transpose, these two values are coming same. And when it is happening, then in that case we call it as a Hermitian matrix. Okay. uh, so I think how to take the Hermitian, like how to find out the Hermitian matrix, let us
A conjugate transpose and A transpose conjugate, both are same.
both are same, yes. So let us we'll try to see that also. Let's say I'll take the same example as used in the lecture, 2, maybe 3 I, or you can actually take any example, right? So it's fine anyway.
Yeah, another example you take.
Psi and let's say 0, or don't take 0, 1. Okay, if this is matrix A, we have to verify whether it is uh, Hermitian or not. How to do that? Like first of all, try to find out the conjugate matrix. So what is the definition of conjugate? Wherever we find the complex number, we'll try to change the sign,
Sign.
right? So what is the sign change? So
2
2,
minus I,
2 minus I plus I
I
1.
1.
and what is the transpose of this? Then it will be
2I and
2I
minus
minus
I1.
I
1,
1.
right? And is it looking same as that of A?
Yes, sir.
Yes.
Yes,
Yes.
and hence matrix A is a Hermitian matrix.
Hermitian.
So we'll try to see again, if I take a transpose first, what will happen? So if I take transpose first, it will be 2 minus I,
Minus I
I1.
I
1.
1, right? And what will be its, and after that, I will take a conjugate. So conjugate means wherever I'll
2
see the complex number, I'll change the sign. So 2 I,
I minus I 1.
and if you see that these two are also equal, and again if both of them are equal to A, then matrix A is called as A is
Hermitian.
Hermitian matrix, right?
Or symmetric complex.
No, this like, there is a, but yeah, it's kind of a symmetric matrix, but in terms of in a complex space. Sometimes you can say that symmetric matrix also an Hermitian matrix, right?
Okay.
Because if you have a matrix which which consists of all the real numbers, if you take its complex conjugate, the matrix remains same, right? Because we don't
Only
change the
for the
sign of the real numbers. We just change the
only
number.
only
Yeah.
only for the square matrix it is valid, no?
Which one? Yeah, yeah. That is
Only for the
because
square matrix.
you can't uh, take
Yes,
the,
yes.
like you can't have the transpose. If you change the if you take a transpose, then what will happen to it? The rows will become columns and
Yeah,
columns will become
of
rows. Then
course.
the dimensions of the matrix will change, right? If you
So
don't have the square matrix. So anyway,
not
that will
possible.
not apply well. Yeah.
Correct, correct.
So, like in summary, again, I'll write it. So, Hermitian matrix will be when A star equal to A. Basically, uh, A star is complex conjugate transpose or transpose conjugate. Okay, fine.
Yes.
There is another term like skew Hermitian, and I think you had that in skew symmetric matrix also. But yeah, you can just maybe you can just see that later on. Okay. Okay, fine. So we'll see some properties of Hermitian matrix. Um, what are the properties of the Hermitian matrix? Properties. Sorry. First is I'll write down all the properties and then we can maybe you know discuss about them. So first is uh, all eigenvalues of Hermitian matrix
Real.
uh, are real. Okay. Then second property is eigenvectors corresponding to different eigenvalues, right? Different eigenvalues
Orthogonal.
are orthogonal. So, have you seen the same properties for the symmetric matrix? Or yes or no? We have seen the same similar properties for the uh, symmetric matrix as well, right? Symmetric when A equal to A transpose. Is that correct?
Yes.
So that means if you know the properties for symmetric matrix, you can actually use that analogy here in the complex matrix. So you don't have to remember for everything. One more property is there. It is not mentioned in the lecture, but I'll just tell you. So Z Az is real for any Z which is in complex space. What does that mean? If your matrix A is Hermitian matrix, and if I multiply it with any complex number, right? So pre multiply and the post multiply, then in that case, its product, right? So that will be a real value, right? So
Complex number.
yeah,
Z is
Z
a
is a complex number. Fine.
it is a Z complex number, complex vector.
Complex vector, sorry, vector. It's not
Because
number. Yeah. So complex
Cn is
space,
the
right?
C
Oh, yeah. That is
complex.
that defined for space. So yeah, it is a vector. So let's say if the vector, if any complex vector, if I multiply with this Hermitian matrix, like pre-multiply and the post-multiply, you will get the real value, right? So yeah. Okay, so that this is not required for our syllabus, but yeah, it is also one of the properties.
Multiply means dot product, no?
Yeah,
Z
dot
dot
product,
product.
dot product.
Z dot product with A, and then the result will be dot product with Z, right?
Yeah, like either way you can do. It's not like the order.
Either
Uh,
dot product
yeah,
A Z or
yeah,
then take
yeah.
okay.
That is like normal multiplication you do, right? So you can do the normal multiplication. Okay. So maybe okay, that is one property. These things are done. Then okay, diagonalization in real case. What do you say for diagonalization? When you say the matrix is diagonalized in real scenario.
Diagonalization we do not understand in the lecture also.
No, no, the complex diagonalization, leave it, leave the complex diagonalization. In general, in real case scenario, we have discussed in the last week, right? What is the diagonalization? Or when we say that matrix A is diagonalizable. Okay, maybe I'll recap it. So, uh,
Mhm.
a matrix A is diagonalizable. And what does that mean by diagonalizable? Diagonalizable is if there exists a matrix like S, right? So S inverse AS
Yeah,
equal
yeah,
to
yeah, yeah,
a
yeah, yeah.
diagonal matrix, right? Is that correct? That is what we said, and this happens when your matrix A uh, is having uh, all
Real
distinct,
eigenvalues.
distinct eigenvalues, right? Real is fine. I'm just talking it about real matrix. So we said that if A is having distinct eigenvalues, that what does that translates? It will have independent eigenvectors, right?
Linearly independent.
Yeah, if your matrix A is having distinct eigenvalues, in that case you will have linearly independent eigenvalues. Sorry,
Eigenvectors.
eigenvectors, right? So if you have linearly independent eigenvectors, then you will be able to find a matrix S such that if I do this S inverse AS, I'll be able to get a diagonal matrix. Is that correct? Or like any other way around is like A can be factorized into this matrix, right? So let's say what is it? S D S inverse. Is that correct? That is what we have seen last week also, right? I hope you remembered it.
Yes, sir.
Correct?
Yeah.
And this is possible. So most of the cases, if your matrix is symmetric, in that case we know that its eigenvalues are real, right? Is that correct?
Yes.
Uh, and what we said is in the properties of Hermitian matrices, we said that all eigenvalues of Hermitian matrix are real. I think this part is fine, right?
Sir,
Yes.
Yes.
the matrix A is diagonalizable.
Huh.
Slide down, sir.
Huh.
The condition is that for the diagonalizable,
Hmm.
A must be symmetric.
Doesn't require, right?
Doesn't require.
A has to be, but A has to be a square matrix.
A square matrix, it should be. Condition
Yeah,
is first a square matrix.
yeah, it's
And
a
it
square
must have
matrix.
the distinct eigenvalues.
Correct, correct. If it
Right.
is having distinct eigenvalues, or no, the condition. Okay, the condition to become A as a diagonalizable is A is a square matrix. That is first,
Like, yeah,
and second condition is which is very like the it is also a necessary condition, which is all eigenvectors
are distinct.
are linearly independent.
Sir, they are
If,
orthogonal.
if, no,
Orthogonal is not required, right? So
if
they should be linearly independent is required for diagonalization.
No,
if they are distinct,
Hmm.
then they will be linearly independent. Na?
No, no, distinct is eigenvalues, right?
Yeah.
Eigenvectors, see, if your eigenvalues are repeated, right? So sometimes I think I have said that also. If you have the same eigenvalues or repeated eigenvalues, in that case also, you will be able to find the distinct or you will be able to find a linearly independent eigenvectors. Okay, just give me a minute. I'll maybe if I have any example, I'll show you that to you.
Yeah, you showed it, but we missed it that.
Okay, but maybe I'll tell you how to do that. Okay.
The last class, I think you've shown it already.
Yeah, last class. That's what. But I think you guys have forgotten. So like some of you. So because see, if that you understand, then this part is like fairly straightforward. There is like
Okay.
nothing different. And what do you mean by linearly independent eigenvectors? So suppose you have u and v and w eigenvectors. So in that case, when I say that u, v, and w are linearly independent, if three vectors are given to you, when I say they are linearly independent, what is the definition? You know,
They are
That
orthogonal
means
each other.
Their linear combination,
yes, C
it's not
C
zero.
digit is zero, no?
It's not zero.
is
The
zero or not zero?
zero.
It's zero.
It should be equal to zero.
The
Then they
constant,
are,
all constants should be zero.
yeah. So that means this, then that case it will be linear, or there are other means, right? What does that mean? Another way to look at it is what, they are not you know like they are not
Linear
equal
combination
to,
of each
yeah,
other.
they are correct. So that's what it is saying, right? If this will happen only when your um, so I think that is the definition of your linear independence. Again, you can say that, let's say you are one vector, it is not along that same vector, right? uh,
Yeah.
along that vector, that also you can say that. But and if it is in a matrix format, what does that mean? When I say that, let's say if I put all of these vectors into a matrix format, let's say you have S as a vector, and sorry, S as a matrix, and you have kept all these uh, uh, you know vectors into the matrix format. What I say about its rank, uh, to if I have to say that they are linearly independent to each other,
Full rank.
Full rank.
so rank of S should be equal to, let's say, whatever the length of the vector is, right? So that means, yeah, let's say it should be a full rank matrix. If it is a full rank matrix, then they are linearly independent to each other. Is that correct?
Yeah, yeah.
All of these property has to be satisfied. But again, the case is what we are saying, that if you have distinct eigenvalues, then your eigenvectors corresponding to those distinct eigenvalues, they are linearly independent to each other. But if you have the repeated eigenvalues, so the matrix A might or might not have uh, linearly independent eigenvector. So sometimes it is possible that with the repeated eigenvalues also will
Okay.
get different eigenvectors, right? Or which are linearly independent to each other. But sometimes if with the repeated eigenvalues you will get the same eigenvector. So that means if you get the same eigenvectors or dependent eigenvector, in that case that matrix A will not be a, or that matrix A cannot be diagonalizable, right?
Okay. Okay,
uh,
sir.
I, I hope you got the idea. So when the matrix A is called diagonalizable, when yeah, when this is the condition, actually these are the two conditions, right?
Two conditions are there. A square, it should be a square matrix,
Huh.
and all the eigenvectors should be linearly independent.
Independent. And if the matrix A is having distinct eigenvalues, then in that case definitely it is definite that A is diagonalizable, right? If they have repeated eigenvalues, then you will have to check whether the eigenvectors are independent or not. Fine.
Okay, okay.
Okay.
In that case, maybe or may not be.
Yeah, correct. Now
But if the eigenvectors are linearly independent, then all the eigenvalues will be distinct. This is correct.
can you just repeat it once more?
If all the eigenvectors are linearly independent
Huh.
of some matrix,
Huh.
then there will have all the distinct eigenvalues. Is it?
No, right?
It is not.
The other way around is okay, not correct, right? Okay, I'll write down
Okay.
two sentences again, maybe. So
Last time in the class you told the reverse is not true.
yeah. So okay, the thing is, I'll write down two sentences. One is, if A is having, let's say, maybe this distinct eigenvalues, that means A will have uh, linearly independent. Okay, so linearly independent eigenvectors. Okay, this is fine.
Yeah. Yeah.
The second sentence will be if A is having
Repeated.
so repeated eigenvalues then in that case A may or may not
Okay.
have independent or linearly independent what is it eigenvectors, right?
Got it. Got it. Okay.
So if a matrix will have linearly independent eigenvectors, the reverse will not be like it will always not have distinct eigenvalues, right? Because with the repeated eigenvalues also you can get linearly independent vector. But if this is the case, right, then that means A is diagonalizable definitely, right? So diagonalizability condition will so A is diagonalizable.
So for checking, we have to, if you get the distinct eigenvalue, then you will directly say that it is limited.
Yeah, yeah.
If it is repeated, then you have to check whether
Check
it
for
is
the eigenvector. So once you, let's say you have a matrix A, you will find out its eigenvalues first. And if the eigenvalues are distinct, you don't have to go for finding out the eigenvectors. You can directly say that
correct.
A is diagonalizable. But if you find out the repeated eigenvalues, then you will have to find out its eigenvectors for each of the eigenvalue. And if you find out they are linearly independent to each other, then in that case, then you can say that it is diagonalizable. If not, then definitely it is not diagonalizable. Is that correct?
Okay. Okay,
So,
sir.
so whatever this discussion has happened for real matrix previously, right? We can use the similar discussion to understand the diagonalization of uh, you know matrices like the complex matrices. Uh, what can we say like similarly now if okay, first thing we know that Hermitian matrix will have real or it can be said to be a symmetric matrix, real symmetric matrix. Uh, Not real symmetric, we can by analogy we can say that Hermitian is equal to let's say the real symmetric matrix. One case is another thing is we know that Hermitian matrix will have real eigenvalues, right? Now, if again the same, can we say the same thing about it? Like if the Hermitian matrix will have the distinct eigenvalues, will that be diagonalizable? Yes, right.
No, huh?
Yes.
Yes, yes. Same thing we can say, right? If Hermitian matrix will have the uh, distinct eigenvalues,
Yeah,
one
yeah, yeah, we can say
can say
because it
that
is
is
no
correct.
need to check because that will be linearly independent.
Okay, so that one thing you just keep in mind. In between, I'll just do one more thing here is okay, we'll have one more discussion about uh, unitary matrix, right? I just left it in between. So okay, keep that thing we have said till now in mind, and first I'll try with okay, we'll see some another special matrix which is called unitary matrix. Unitary matrix. Okay, what is unitary matrix? Uh, First thing is it should be a square matrix. Okay, if it is a square matrix and it will have ortho normal columns. What do you mean by orthonormal columns?
Each and every column are orthogonal to each other,
Yeah, and what else?
and the length of the
Correct.
each column is one.
Right. So that was we have seen for real case. What was the thing for real scenario? Real vectors or real space? Which matrix have you seen that kind of matrix previously? Yes, right. We said Q transpose Q should be equal to if this is equal to I, then
I
in that case, and if it is orthogonal, in that case, Q inverse is equal to Q transpose that we have seen. And one more thing is the vectors in that Q, right? They are or the columns of matrix Q, they are orthogonal to each other and their lengths are equal to 1. Similarly, there is a matrix called unitary matrix in complex case that will be it is denoted by U. So U star U should be equal to I. And what is U star? Okay,
U
and
U
that should
conjugate transpose.
U bar transpose.
yeah. So
U
U conjugate or transpose of conjugate, whatever you can say, right? So and
U
this U,
inverse. This is inverse.
inverse is equal to, then in the see like likewise you can say, right, if it is a unitary matrix, then U inverse should be equal to U star. In this case, when we say that they are ortho normal to each other, this two matrix Q, in that case Q inverse is equals to Q transpose. Similarly, if the matrix is unitary, then in that case U inverse is equal to U star. Fine.
Hmm.
So its inverse basically will be coming same as that conjugate transpose of that matrix. Fine. Okay. So here U is a unitary. This matrix also is very important. Uh, what it is like, how to see that? Like maybe we'll take the same example from the lectures and try to see that we have understood it properly or not. Okay. So if you have U matrix 1 by root 2 and I by root 2, and here by root 2 and 1 by root 2. Okay, is it a unitary matrix or not? How to understand that, or how to find it out? That first case is you'll have to check uh, these columns are orthogonal to each other or not, right? Is that correct?
Yes, yes.
So how to check this? So okay, maybe I'll try to show you.
Transfer
Let us say it is
transpose of
U1.
we will take the transpose of the first column
You
and
will you will find out U1 transpose
yeah,
U2 equal to 0 or U bar transpose U2 equal to 0.
yeah.
That
U1 star U2 is equal to 0. We have to check.
right, no? So
Am I right now?
correct. So in this not U star you cannot say because uh, it is denoted for the uh, matrix, right? We are just looking at for the vectors now, right?
This we are checking for orthonormal
Columns,
columns.
orthonormal columns, right?
Can we directly check also this matrix directly? You take U star U,
Uh,
it gives identity, then it is
should
okay.
Yeah, that is also okay. That is fine.
But that is easier to check U1 transpose, right?
I will not say like that, but you can just think about, like, we are just cross checking whether whatever we are saying is correct or not. It's
Okay,
not
okay.
like you can use like any other way. That's like it will take the same amount of time to compute, right?
Okay, okay.
Yeah. So can you just check what is the uh, answer here? So
1 by 2,
I by 2.
I by 2
I by 2.
and minus.
minus I by 2.
Minus 1.
So will that give me 0? And can you, what do you think about U2 trans or U2 transpose U1? That will also give me the same thing, right? That should be giving me the same thing. Is that correct or no?
Yes, sir.
Right.
Sir, why you written minus I by root 2?
So basically what you are checking here, they are orthogonal to each other, right? So how to check? Generally, how you check in real case? U1, the dot product between the two vectors is equal to 0, right? Or in other words, U1 transpose U2 equal to 0, right? But in
Yes,
complex case,
sir.
what we said, the dot product, how should we do? We'll have to take a conjugate and then transpose and then multiply with another vector. Is that correct? That's what our discussion at the start of the session, right?
Yeah,
Yes,
yeah.
sir.
So that's why I have taken that minus here. Fine.
Yes, sir.
Okay. And what is another condition? So this says that these two vectors are orthogonal to each other, right? So this says that orthogonal to each other. What is another condition to check whether they are normal? So we'll have to find out its length, right? And what is how to find out its length? So we'll have to take square root, but I will do it later maybe. I'll try to find out its norm square. So it will be uh, again it will be 1 by root 2 minus I by root 2 and 1 by root 2 plus I by root 2, right? Is that fine?
Why, sir? Maybe
Okay, what is the length of any vector?
x dot x.
X dot x. So let us say, yeah, let us say if your x, right? So it should be x dot x, right? But in complex case, what you how you write this x dot x?
X bar.
X
X
bar
bar trans.
transpose x, right?
Okay.
And in real case we say x transpose x, but in conjugate like when complex is there, see that is what you have to understand. That's the only thing where you otherwise you will get zero. We'll try that out also, but yeah, can you just tell me this product first? So it
So,
will be, yeah.
so why you
Half
transport
plus half.
U2?
What is the length of any vector? Length of vector, what is it? Root of
Root of x1 uh, x into x.
no, that is correct or no? Okay, first please. Okay, let us say you have vector, maybe I'll say that u is equal to 1, 2. What is the length of u? How will you find out generally? You
Root
take
of
square
1
root,
square
1 square plus 2 square,
2
right? That is
square.
root of 5. But isn't it the same as that of writing u transpose u? Let's say 1, 2. So it is 1, 2. And I'll say that square root of later on. So what is this? What is this? This value is
1
5.
plus 4. Yes.
So u transpose u gives me 5, but I want its length. So if I take a square root of this, I'll get the same thing, right? So basically, the length of any vector is equal to square root of the dot product between that vector itself, right? The dot product
Yes.
between the vector and its vector, again, between that vector itself. So that is basic definition of our length of the vector. But we know that in complex case, we cannot uh, do this square root of u transpose u. Instead, what you have to do? You'll have to take the conjugate,
Take
Yeah,
conjugate.
conjugate. U bar transpose.
right? No, why? Because if you see that, if you just multiply it, right, you'll get the answer 0.
0.
Yeah, so that is what we have to avoid it in the complex case. Okay, what is the now? So here it is conjugate, right? Conjugate of the first vector. This is my first vector, 1 root 2 and I root 2, right? This was u1. Is that correct?
Mm-hmm.
Is u1. So how to find out its length now? u1 conjugate transpose u2.
So we have to transpose the U1 vector only now.
Huh. So I have transposed it, right? But with conjugate. And I have to multiply with u1. Not
Okay.
understand? You understand it or no?
Yes, sir, got it.
Okay. So 1 by root 2 into 1 by root 2 is 1 by 2 uh, plus
Sir, there will be minus, no?
because I have to take the conjugate. So conjugate is minus here, and that's why it is. If I don't take conjugate, it will be 0, right? So now minus
I square by 2.
I square
By
by
2.
2. So that will be 1 by 2. Minus I square is
Plus
minus 1.
1.
Okay, plus 1 by 2. So that will be
Plus
1.
1.
So that
1.
means the length of u1 is equal to 1. So that means it's of unit length. Similarly, what is the length of u2? So length of u2 will be u2 is what? I by root 2 and 1 by root 2. So it will be length of u2 will be equal to what it should be equal to? Square root of u2 conjugate transpose u2, right?
Hmm.
And what is u2 conjugate now? Minus I by root 2, 1 by root 2, and that vector. So it is I by root 2 and 1 by root 2. I hope this is, till now, this is okay.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
fine. So what is the uh, multiplication now? So it's like
Minus I square
I
by
by
2.
2 minus I square by 2 plus 1 by 2.
2.
So again it will be equal to 1 by 2 plus 1 by 2
1.
One.
equal to 1. So that means both of these vectors are unit vectors, right? So this u1 is unit vector, u2 is also unit vector, and they are orthogonal to each other also, and that says that these two columns are orthonormal to each other, and if the uh, columns of the matrix they are orthonormal to each other, then we call that matrix u as unitary matrix, right? Another way to check this as is this is the definition, right? So u star u should be equal to 1. Let's try to find out that also. So what is u, matrix u? It is
1 by square root 2
I by root 2 here, and
minus I.
I by root 2 and
1
1
by
by
root 2.
root 2, right? One of the I think one of the important thing about Hermitian matrix also is that I think I have didn't say that time, but the diagonal entries of that matrix should be for our
Equal.
matrix,
1.
not real. They shouldn't be complex, right? Why? Because if you have the complex values at the diagonal, then when you take the transpose, right, the values will change. I think so, right? So I don't know. Okay, maybe I'll when I'll talk about diagonalization at that time again I'll say about it, right? So fine. Okay, so not that is our concern. So what is u star here? What is u star? It is u conjugate transpose.
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 So that will be equal to 1 by root 2 minus
Minus
I by
I.
root 2
Minus I by root
minus
2.
I by root 2 and
1 by root 2.
1 by root 2. Fine. And that is also your like final conjugate, right? So because if you take the conjugate it will give me the same thing. Now what we said is it is called unitary when u and u star, right?
I.
Is equal to I.
Identity matrix.
Yeah, so sorry, I think I just missed it. Oh, it should be u star to u. So what is u star? 1 by root 2 minus I by root 2 here, by root 2 and 1 by root 2. Now what is u? U is 1 by root 2 I by root 2 by root 2 and 1 by root 2, right? Okay, so what is the multiplication? So it's a 2 cross 2 multiplication, so I'll get what? 2 cross 2 only, right?
1 by 2 plus.
So here
Sir,
1 by
here
2,
is minus now.
where?
Minus I by root 2. Sir,
Yeah,
in
yeah,
U star matrix.
correct, right, correct. So what is the first row or first element in this?
1 by 2 minus I square by 2.
So that is 1, right?
Hmm.
Here second element will be the first row and the second column. So that is I square, so that is I by 2
0.
I by
minus
2 minus I
I
by
by
2
2.
is
So that
0.
is 0. What about the third element? It is the second row of the first matrix multiplied with the first row of the
minus I by 2
First column, yeah. So minus I by 2 plus I by 2, 0,
plus
and
plus I by 2,
and the
0,
the last element will be I
One.
square,
1,
I square by 2, and that is, yeah, minus
1.
1. So that is equal to,
Okay, identity matrix.
and then I can say that U is
Unitary.
Unitary matrix.
done. So I hope you understand how to find out the unitary, how to say that if whether matrix A U is unitary matrix, right?
Mm.
Okay.
Yes, sir.
Okay, so all of those concepts are fine, I guess. So length, what about the length and all?
It is better to check this one, no? Because in one shot we get the unitary also and diagonalization also, right?
Hmm. No,
It is
yeah,
better to check.
no, not required. You can just say that diagonalization is, we haven't talked about it, right, as of now.
Yeah, unitary.
Unitary is different case. So, okay, that is it. One thing about that. What are the properties? Eigenvalues of unitary matrix will have absolute value 1. Okay, that maybe I'll talk about those later on. It's not okay. What are the topics I should cover is, okay. So maybe I'll talk about spectral theorem, the Schur theorem and spectral theorem, and then maybe we can talk about unitary matrix once again. What are its properties? I haven't shown you any properties here about unitary matrix. We'll see that at the end, right? So first of all, I think you should know about the Schur's theorem and spectral theorem. Okay.
And properties of the Hermitian matrix only we have to remember that this is the property. Proof is not required, no?
Proof is not required. If you understand proof is fine. If you, it is not required anyway. It's like if you remember the property, that's enough, right?
No.
Proof are, it's already there in the lecture slides, so you
The
can just,
lecture it is there, which is complex type of thing.
no, if you understand the basics of the complex matrix, I don't think that is like very tough proof to understand, right?
Mm-hmm.
I'm not covering that. We'll try to. So what I'm trying to show here is, I'm not actually covering everything in the lecture. What I'm saying is the basic understanding of all these topics, right? We are actually discussing it. Like I'm not like kind of teaching you most of the things. What we are doing is we are kind of discussing here, right? So yeah. So okay. So there are what we have seen till now is a star is equal to, when a star is equals to a, then we call it as
Hermitian matrix.
Hermitian matrix. What is A star? It is complex conjugate transpose. Okay. And what is the property of unitary matrix? That U star into U, if it is equal to A, I, then it is, then U is,
Unitary matrix.
yeah. So maybe I'll write only unitary matrix. Fine. Okay. Let us see about the diagonalization of this matrix. So there is a theorem called Schur's theorem. It says, I'll write down the theorem first place. It is a square matrix, or a n cross n matrix is, so n cross n matrix over Pn. What is this? In the complex space
In the complex space.
is similar to a triangular matrix.
Sir, upper triangular.
Upper triangular also, yeah. I'll write down it, and then maybe you can just I'll tell about it. Right? It's okay. Upper triangular and lower triangular is like kind of a not much difference it will make, right? So because we have the decomposition about LU decomposition, have you heard? I don't know. Okay, maybe I'll not go there.
Lower upper decomposition.
Yeah, but how to do that? Maybe that is a different. It is not covered in our syllabus, possibly. Fine, it's okay. So it is similar to a triangular matrix via a unitary matrix. I'll write down the definition first, and then we'll discuss over it. Such that it is there exist unitary matrix U, such that U star A U equal to T, and where T is a upper triangular matrix. Right now, it's fine. So T will be your upper triangular matrix. What does that mean? If a square matrix is given to me, right, the square matrix is similar to a triangular matrix via a unitary transformation or via unitary matrix. Is that so? There exists a matrix U such that if I have this U star AU, the multiplication of U star AU, I will get a upper triangular matrix, right? That is the uh, meaning of it, right? And what we said about the diagonalization. Okay, what is that diagonal matrix will be there? So the diagonal matrix will be a matrix with diagonal entries, and elsewhere it is 0, right? I hope that is fine.
Pardon, sir, once again.
So what is the diagonal matrix? Diagonalizable matrix. So diagonalizable matrix is like if I have a matrix A, and if I
Yeah.
multiply with that S inverse, or if I do the multiplication between S inverse AS, I'll get a diagonal matrix, capital D, right? But the diagonal matrix will be a matrix. What is the diagonal matrix basically? It will have entries along the diagonal, and uh, other entries, right? Apart from the diagonal, they are all zeros, right? Maybe in the upper triangular region and the lower triangular region of the diagonal. But here in Schur's theorem, what it says is you will get a triangular matrix such that the U star AU will be equal to the triangular matrix. That's fine. Okay, right.
Screen, sir. Yeah.
Okay, that is the theorem. We'll try to see like how to do that maybe. So the proof is given to us.
A must be a n by n matrix of the complex space.
N by n is a square matrix.
A square matrix. Similar to a triangular matrix via a unitary matrix.
This is the unitary matrix.
What does it mean? Via
the unitary matrix means there is some unitary matrix U. Like you have to find out that kind of unitary matrix. If you have that unitary matrix, so when I said the diagonalization, right? What was the diagonalization of the matrix? We said, right, it is S inverse AS equal to D, right? So the definition will be like this. Like let's say you have a n cross n matrix in maybe let's say real space is similar to a diagonal matrix via like matrix S, right? But S was what? How you found out S? We have S is a matrix with the eigenvectors, right? Corresponding to its distinct eigenvalues, or maybe or the it is a set of eigenvectors which are linearly independent to each other, right? So we have found out some S such that we will be able to find out its a diagonal matrix, right? Similarly, we have to find out such an unitary matrix. If I use that matrix to do this calculation, I'll get a upper triangular matrix. So every square matrix, right, will be maybe I can say that it will be a similar to a upper triangular matrix, such that there will be some unitary matrix existed. So you have to find out that kind of unitary matrix. Is that fine? So how to find out that unitary matrix? That is, there is a procedure to that, right? And I
Okay.
think it's a long procedure. I think that is what you guys have not understood, right? Maybe
Yes, sir.
Yeah, that you could
how
not
to
understand.
solve that. So I'll take that example itself, maybe, and then we'll try to see that, and then we'll have one more. Let's spectral theorem. Once you understand, I think this the spectral theorem is like more simplified version of this Schur's theorem, right? Because spectral theorem,
Sir,
yeah,
S is a matrix with eigenvectors of A.
yeah, linearly independent eigenvectors of A, right? This is condition of
Diagonalization.
right. So that when you'll have to find out the set of independent eigenvectors. If you don't have that set of independent eigenvectors, you will not be able to find out that diagonal matrix, right? So if it is A is n cross n eigenvector, sorry, n cross n matrix, how many independent eigenvectors you will need to formulate S?
N?
N, right? If it is n minus 1, will that be possible then?
No.
No, right? So that means if you have n minus 1 eigenvectors of A, which are linearly independent, then A will not be able to, like, you will not be able to find any diagonal matrix for that A, right? So that means A is not diagonalizable. The condition is very uh, clear, is that if you have n cross n matrix, you should have n independent eigenvectors. If you have n independent eigenvectors, then you will formulate, you'll take all those n independent eigenvectors, put into a matrix. So how to put it into the matrix? You'll just like you just add all the columns, right? And to create a matrix S, and now you take its inverse, just do this multiplication S inverse AS, you will get that diagonal vector. But the diagonal is, what is it? What is the diagonal matrix?
Eigenvalues.
All the eigenvalues along the diagonal,
Diagonal.
right? Correct?
Yes, sir.
Everyone is fine with, see, if you understand this part, I think then only you will be able to understand the next part, right? Because you, that's kind of a similar thing, so what you are doing there. Okay, shall I proceed further if you don't have any questions here?
Sure, sir.
Okay. Okay, so the maybe I'll maybe we'll see those uh, this part, right? I think you guys were having issues this part. So basically, this was a definition for diagonalization, right? That is for unitary matrix. This is the part is where, okay, sure, there, right? What it is saying now, you have to find out U, right? You have to find out this unitary matrix U, and the procedure to find it out is what you have to do. This is, let's say this is U1, right? The first U1. What is its combination? So right, in diagonalization, what you did, you took all the eigenvectors, correct? Correct.
Yes.
Yes, sir.
Here, what we are doing, are we taking all the eigenvectors? No. Let us say we are taking only one eigenvector, uh, and we'll have to find out its basis, which makes it orthogonal. So here, Z1 is what? It's one of the eigenvectors of this A, right? Matrix A. Possibly eigenvector corresponding to maybe the highest eigenvalue. You can take any one, but let's say we have taken it like the first eigenvector. And what you do then? We found out its orthogonal basis, right? Okay. You don't have to worry about all of this right now. Just try to understand here. So this Z1, U and V are what? they are orthogonal to each other. Is that correct? Z1 is what? Z1 is the eigenvector of A. We have found out, then you have got like two eigenvectors, not eigenvectors, two other vectors which are orthogonal to, let's say, Z1, and orthogonal to Z1 is basically is what? Z1 star U, Z1 star V, and U star V should be equal to 0, right? That is the condition of orthogonality. Okay. What is next? Uh, A into U1 is equal to what? So basically A, if I multiply it with this U1, I'll get AZ1, AU, and AV. Is that fine? This part is fine?
Yes.
Okay, so AZ1 is basically, I can write it
Lambda
as
Z1.
lambda 1 Z1, right? Because we know that eigenvectors from eigenequation, we can write AZ1 equals to AZ, lambda 1 Z1. So that vector, the first column will become lambda 1 Z1. The other two columns will remain as AU and AV, that multiplication. Now, let us say this was your U1. What do you do later? You will take the uh, conjugate transpose of u1, and then you see what will be the conjugate transpose then. If u1 was z1 u and v, the conjugate transpose will be, so z1 will become row now, u and v also will become rows, the transpose one, but then you will have to take its transpose. So now z1 transpose, z1 conjugate transpose, you so all of this will be there, and this is au1, which is lambda 1 z1, au and av. What will happen now if I take uh, the multiplication? So the first row of this is multiplied with this row. What I'll get now? Okay, maybe I'll write it down so that it will be understandable. So what is this? Sorry.
Sorry, better you can take an example.
Yeah, I will take it. First, try to understand this, and then
Yeah.
we'll take
First,
that
first,
example.
first, first this one, then we go to example and verify that.
So Z1 conjugate transpose is U conjugate transpose, and let's say V conjugate transpose, right? And what was the product here? It was lambda 1 Z1 AU and AV. Is that fine? That was the product, right? And this entire thing is U1 star A U1, or not the small one, the capital one. So it was
Sir,
a
we find the eigenvector of first column only.
first column. We can't find the eigenvector of first column, right? It's the matrix, the eigenvector of matrix A. If only one, we have taken one eigenvector. That's it.
Why did we take it only one? What was the
See,
reason?
see that.
Procedure.
It's a procedure, right? Like likewise, we
Okay.
said for the diagonalization, what we did is if we took all the eigenvectors of A, right? That time.
Okay.
Similarly, we are just taking one of the eigenvectors. Okay. Now, uh, what will be its product? You will have to tell me. So so first will be what? First row and the
Just
first
one
column.
question. Instead of lambda 1, you could have taken lambda 2 or lambda
Yeah,
3
that
or
is fine.
lambda 4.
That is fine. You have to take
Whatever,
one of the eigen.
any lambda we can take.
Yeah, you will have to take only one eigenvector. Yeah, with respect to any lambda. That is fine.
In
Yeah,
the
what I'm
first,
asking is, I can take any
in the
lambda.
Yes.
in the first column, no problem.
So what will be its, so first element will be what then? Or
Z1 bar transpose into lambda 1 Z1.
can I say it will be uh, lambda 1 times Z1 bar transpose Z1? Is that correct?
Correct.
But what is its, so if you just see that, what is then uh, Z1 transpose Z1? What we have done is we have taken its unit vector, right? So when we got the eigenvector, we have taken its unit vector. So this part will become what? Equal to 1.
How?
Okay. So how is not is the thing is when you say this, let Z1, U and V, right, be the orthonormal basis. There is a mistake here, which is like it is said to be it is equal to 0, right? So the length of Z1, length of U and length of V should be equal to 1. Then only this will become orthonormal, right? And this
So,
product is equal to,
the
yeah.
length was written is 0 there.
No, that is, I think there is a mistake. It should be equal to 1. Okay, because then only it will become orthonormal. What is the condition of orthonormality between
Yes, yes, it
Yeah,
should be
yeah,
equal to 1.
it should be 1. It
and
should
the
be
product
1.
is equal to 0? I think
0.
by that is a typo there, so
Okay, okay.
that should be equal to 1. So by that thing you can say, right, it's equal to 1. So Z1 transpose Z1 is basically it's the length of that vector, right, Z1 vector, and then your value will be lambda 1 here. Is that correct?
Mm-hmm.
Okay, so yeah, okay, now what is the uh, element here, this portion? So it should be the second row and the first column, right?
Mm. Lambda 1 U bar transpose Z1.
So basically it should be u bar transpose times lambda 1 Z1. Is that correct? And lambda 1
U1,
is a,
U1,
not u1,
not
so u yeah, u
yeah.
transpose uh, lambda
Lambda
1
1
Z1,
Z1.
but lambda
Yes.
1 is a constant, so lambda 1 I can take it common, so it will
Mm.
become u bar transpose Z1. But we already said that they are orthogonal to each other. So can I say it is equal to 0? That is what we have defined here, right? Z1
Correct.
transpose. So the uh, so when it is orthogonal to each other, right? So we have already seen that when the two vectors in complex case, if they are orthogonal to each other, then Z1 star U is equal to U star Z1, right?
Yes.
Because anyway that product should be coming out to be 0,
0.
right?
Mm-hmm.
So this part will also be 0.
Mm-hmm.
And similarly, what will happen to this part? So that is again this portion will be what? V bar transpose lambda 1 Z1. So basically it is lambda 1 if I take common. So V bar transpose, which is basically V star Z1, and this also will be equal to 0. So can I say these are two 0 values here? What about this quantity here? It will be
0.
equal to Z1 bar
0.
transpose AU. No, it will not be 0, right? Uh,
Why doesn't AU become lambda U, sir?
because U is not a eigenvector of A, right?
Okay.
We have just taken one of the eigenvectors. So that when it will become,
Yeah, that is eigen equation.
so that A Z1 become lambda Z1 is because Z1 is an eigenvector of A, but U is not an eigenvector of A. Basically, U and V are the vectors such that we'll get this. If I take this into the matrix format, like if I just added them into a matrix format, they are orthogonal to they form an orthogonal basis. But U and V are not the eigenvectors of A. Is that fine?
Oh, yes.
Right. So I hope this is like now until now it's clear. So this part will be equal to 0? No, right?
No.
This is
Which
Z1
which one we are getting? Z1
this element will be first row into second column.
But
second column.
why is it 0?
And it's not equal to 0.
No,
It's
it
saying
is
that
not
not equal to
not
0.
not 0 because
Correct,
they are
right?
not orthogonal. Z1 and U
Yeah.
are not orthogonal,
Yeah.
right?
So no, they are not. No,
So
that is
it is not. So it is
no, no,
not 0.
Z1 and Z1 and U are orthogonal. But this case, there is a matrix A involved, right?
There is
Initially,
no
what
eigen.
happened is lambda 1 was the constant value. We would have been like taken common, and then that vector
Okay,
multiplication
okay.
was equal to 0. But here it's a matrix, right? It's a matrix multiplication, matrix vector multiplication.
Mm,
So this
right.
there will be some quantity available. Here, what we done? So
Lambda
U1
1 will be taken
transpose
out.
lambda 1, because lambda 1 is constant, so we can actually either you can multiply into that vector and then take, but it doesn't make any difference, right? If I multiply any constant with a vector, what will happen? Its length either increases or it shrinks,
Decreasing.
but
Yeah.
it will be a same vector. So if one of the vector is orthogonal to another vector, right, let's say is z1 and this is u, if they are orthogonal to each other, so lambda 1 z1, which is along this line, right,
Stretch to original.
still either it will stretch or either it will shrink depending on the value of lambda, since it's constant, but it will always be orthogonal to that vector u,
U.
right. So that's why we were able to say definitely about these two quantities, they are zero, fine. But
Hmm.
this cannot, I cannot say anything about it. There is some quantity, right? We'll get it. Similarly, what about here? This will be Z conjugate transpose AV. Is that fine? Okay. And similarly, we have some other quantities here. What it will be? Like it will be U bar transpose AU. Here maybe U bar transpose AV. Here, what is it? V bar transpose AU and V bar transpose AV. Is that fine? Hmm?
Yeah, yes, sir.
Yes, sir.
So what? So until this part, you understood these two were zero. These are some values, and this is called as a matrix B. Okay, so some matrix B. Again, we have to follow, like we have to follow the same procedure what you have done earlier for this matrix. What you have to do now? Consider this as a matrix B. This thing as matrix B. Okay. So how this matrix will look like now? Can I say that it will look like something lambda 1, right? Here some values. So I'll say that, let's say L1, L2. Here it's 0, 0, and here it is matrix B. Fine. Okay.
Yes.
Now what you have to do is, for this matrix B, you have to follow the same procedure. So now consider this matrix B. What you did initially, first find the eigenvalue of one of the eigenvalues, take one of the eigenvalues, find out its eigenvector, right?
Hmm.
What next? We have to find out its orthogonal basis or orthonormal basis. Okay, is that okay?
How do you find the orthonormal basis?
Initially, okay, that I'll tell you how to find out, but initially we said na z1 and z1 will be its eigenvector and u and v will be some orthogonal basis. So orthogonal basis is basically you need to satisfy these conditions, right? So somehow you,
Yes, any matrix we can take.
any vector you can take, that is like which is orthogonal to uh, that z1, right, or each other. Basically if it satisfies this condition, that will be fine. We'll see through the numbers, but currently we'll have to follow that procedure again and again, and you'll get something like this. So the P star, you'll get some matrix, unitary matrix P again, uh, which gives lambda 2, lambda 3, and if I just do again, right, so all of this procedure, I'll get this upper triangular matrix. How you got it? Let's see. That we'll see that through example. But till now it was fine, right? U star, U1 star A, U1 is this one, lambda 1, and this kind of thing, and then we have B. So what we did for B, we found out another eigenvalue, which is lambda 2 of B, and there is a matrix unitary.
This lambda 2 is of the B.
B, yeah. It is not of A.
Okay, okay.
Okay. It is of
So we have to again calculate the eigenvalue of B.
B. Yes. So it's kind of a tricky part here. Like it's like calculation intensive, but it is like same procedure. You have to repeat it again, and you have to find
And the
it.
unitary matrix P.
Yeah. So and the unitary matrix, if I find it out, you will get this equation like lambda 2, lambda 3, and something like the star. Star means like some values present there. So okay, so now u2 will be equal to, let's say, 10000 p, and u2 star is this 10000 p star. So you'll get that. What is this mean by use p star p equal to I is what does that mean?
Unitary.
P is a
It
unitary
is a
matrix.
unitary
Yeah,
matrix.
P is a unitary matrix, right? Or you can say another way is that yeah, okay, so that is also another case. And then u1 star au1 was the previous matrix. I have just multiplied that u2 star and u2 here, so that okay, this the final thing will be like this, right? So okay, we'll see now the true example, like how this t will be coming. Fine. The first procedure, if you understood, then we'll understand everything, right? Let us try to see this. First, I'll show you here, and then we'll see that whether we can be able to find it out or not. This was the matrix A, right? 5,
Yeah,
5
please.
minus 8, 0 minus 5, 16, 9, and minus 10. The question is, we have to upper triangularize A, right? So, by using the Schur's theorem, let's say. Uh, what are the eigenvalues of A?
Do a step by step, sir, so that we
No,
can do.
I'll do.
Yeah.
First of all, see this one, see this part, and then we'll try to solve it. Okay. Uh, if I do the characteristic, like we can do this characteristic polynomial, we can find it out. What are the eigenvalues of A then? 1 minus 3 minus 3, right? It will have actually 3 eigenvalues, but yeah. So 1 minus 3 minus 3, it will be a repeated eigenvalues. The eigenvector is found out, uh, you know, corresponding to 1, lambda 1 equals to 1, and that comes out to be, let's say, minus 2, minus 1, and 1. So minus 2, minus 1, and 1, uh, and we got some basis here, let's say 1 0
How
0
did,
0 1 0.
see how this matter? Eigenvector
Which
minus
one?
2, minus 2, minus 1, 1.
How to find out eigenvector, you're saying? Okay,
Yeah,
I'll
first,
show you. Okay, I'll show you. That is the all basic
first.
procedures we have done previously.
Determinant of A minus lambda I equal to
Huh.
0.
Okay,
That's it.
got it, got it.
Fine,
Oh,
right?
got it. Yeah, got it, got it.
So that's how you found out like first eigenvector, which is minus 2, minus 1, 1. We have taken the basis, like let's say 1 0 0 and 0 1 0. They are definitely orthogonal to each other. You know Smith procedure, right? I have
Yes, Gram-Schmidt.
Gram-Smith procedure. All of you know, right? Or you forgot?
We know, but we
We
do
know.
not calculate.
You don't know how to calculate.
Forgotten,
Yeah,
sir.
Okay. Okay, fine. So let us say I'll take the example of this and we'll
yeah.
see
Please
it
do the
later.
step,
Okay.
steps, sir, steps. Please.
Okay. So what is your Z1? Vector Z1 is minus 2, minus 1 1. Okay, this is my Z1. E1 I said as 1 0 0. Okay, we actually can find out the unitary, like the value of Z1 as like unit vector. We can directly find out, and then also you can do, but sir has done like this, so I'm just using the same values and 0 1 0, right? Okay, so we have to find out the orthogonal basis, right? So these are the three vectors. We have to find out its orthogonal basis. So are these, first of all, are these vectors orthogonal to each other? Let us try to see. So how to find out they are orthogonal to each other? So minus 2, minus 1, and 1, and 1 0 0. What is the value here? Minus 2,
Minus
right?
2.
So that means Z1 and E1 currently they are not orthogonal to each other, right?
Yes.
What about Z1 and E2? Again, it will give you value minus 1. So that means it is not orthogonal to each other. E1 and E2 are orthogonal to each other. You can see that like very clearly, right?
Yeah.
Fine. I hope all of you know this procedure. Okay, but that means Z1 is not either orthogonal to E1 and not orthogonal to E2. So let us try to find out.
Why did we take this E1 and E2 only this 1 0 0 and 0 1 0?
See, you can actually see, that's what I'm saying. You can,
Okay.
there are the ways you have to find out the orthogonal basis in R3, right? So you have taken one of the eigenvectors. Now you have to find out the other two eigenvectors such that they should be like all
Orthogonal.
three. Yeah,
Okay.
they should form the orthonormal basis. That is the procedure. So you
Hmm.
have choice to take any other two vectors. If they are not orthogonal to each other, then you'll have to make them orthogonal to each other. And what is the procedure to do that? The Gram-Schmidt one. Okay.
Okay.
So Gram-Schmidt procedure, I'll just again.
But means we can start with any E1 and E2
Yes.
and
Yeah, and then
okay.
make them orthogonal. And the
So
procedure
can you
is,
show me the original matrix? What is the value? Just
yeah,
slightly up.
yeah,
5 5 minus 3,
this one.
5 5 minus 3, and then
5 minus 8 0
matrix A.
Right. This is the matrix A. 5 5 minus 6. If I'm reading it
Okay, 8
column wise, 8
0
0
1
minus 5, 16
16
9
9 and minus
minus
10.
10. Okay. And it's for one of the eigenvalues is lambda is 1, and the
Minus 3 and this
eigenvector corresponding to it is -2, -1, 1.
1.
Okay. We have taken two other vectors like 1 0 0 and 0 1 0. Now I have to find out its the eigen basis, or maybe orthonormal basis. Okay, how to do that? That is a question, right? So we'll have yeah. Sorry, anybody saying something? Maybe I'll show you how to do that. Let's say uh, if you don't remember Gram-Schmidt method, I'll just go through it once. So let us say you have
recap,
you
sir.
have vector A, right, and you have another vector B. Are they orthogonal to each other, A and B? In
No.
current form, no, right? Okay. I'll have to find out the basis Q1, which is, suppose, let's say A by A and Q2 as capital B by B. Let's say. Okay, what is A and B? I'll tell you that later. First of all, this small a and small b, are these two vectors orthogonal to each other?
No.
No. If I take a projection on that, B's projection on A, then this projection is orthogonal to each other, right? Or orthogonal to A.
Yeah.
So what is this projection? It's
E.
actually its error, which is equal to B minus
B
P.
minus P.
Now, what is this? P is projection, right?
P is a projection of B on A.
Okay, fine. And
Yeah.
this error, I'm just saying that this error vector is basically this one, right?
Mm-hmm.
And this vector, I'm saying it is equal to capital B, which is small, which is same as that of the error vector. Now it's fine. So can I say that what is the value of it then again? Okay, let's say E equals to B minus, or this E equals to capital B, which is equal to small b minus, what is P? What is the value of P? A transpose, or basically A transpose A.
A transpose A upon
No, sorry,
A.
A transpose B upon A
B upon
transpose
A
A.
transpose A into A.
Is that fine?
Yeah.
Huh? Right.
Yeah. Projection of B onto A into A.
Right now.
Correct now?
Okay. That is correct. That is correct. So fine. So
Why did we not write this A transpose A in a
that now I'm not I have just shown you, right, like everything last time. So I'll skip that part. You can just go
Okay,
ahead,
okay,
like,
okay, fine, okay, fine,
because
okay,
it
fine.
will take a lot of time again to
Yeah,
go
okay,
through.
okay, forget, let.
Yeah.
Projection, okay, correct.
So currently, what I am saying is, this A transpose capital B is equal to 0. Is that fine? That should be equal to 0, and that is correct, because B is nothing but my error vector, and error vector is here, it's orthogonal to each other. Right now, how to find out? Now let us say you have a vector. Let's consider this vector, and let's say z1 and e1. Let us say z1 and e1. I wanted to find its so I'll just make sure that, okay, first of all, what we can do is, we'll make this z1 as unit vector. How to make this z1 as unit vector? What is the length of z1?
Divide by its norm.
So it is root 6, right?
Root
Yes.
6.
So I'll say that it's like minus 2 by root 6, minus 1 by root 6, and
1 by root 6.
1 by root 6. Okay. Now think this as like this. So I'll say that I am just taking the projection of E1 onto Z1. So the error vector will be what? What will be the error vector now?
We are taking the projection of E1.
I'm just okay. So
on Z1.
So the error vector, or I'll say the matrix B or vector B, is basically is equal to B minus. So what is B here? This is small b. So like it's 1 0 0 minus A transpose B is what here?
Z1 transpose
E1.
E.
E1, right? So what is Z1 transpose E1? What is Z1 is minus
2 by root
root
6.
6.
Minus 2 by root
Minus
6,
2 by root 6.
Minus
minus
1 by root
root
6.
6, and
1 by root 6.
1 by root 6.
Root 6.
Yeah. And B is
100.
0.
So basically it is
Minus 2 by root 6.
minus it's 2 by root 6. Okay. So here it will be minus 2 by root 6 in the numerator. What will be the denominator?
Root 6.
A is our Z1, right?
Z1.
Okay. So it will be root 6. Okay.
Yes.
Correct. And what is E1? Or what is the A vector A?
100.
No. A vector, na?
A
This
vector
Z1.
is
Z1, right?
Z1.
Okay, maybe I'll write down, see, in these terms, I'll say that it's Z1. This one is E1.
E.
Okay. And now this will be what? E1
E1 minus
Z1.
Z1.
And so accordingly, what will happen now here? E1 minus
Z1 transpose
Z1 transpose E1
E1.
divided by Z1 transpose
Z1 transpose
E1.
Z1.
So basically, it's like length of Z1
Norm of Z1.
into Z1, right?
Yeah.
Yes.
Fine. So I'll just remove this part so that we can understand it better. Fine. So now this is root 2, sorry, minus 2 by root 6, minus 1 by root 6, and 1 by 6, 1 by root 6. 1 by root 6. Okay. So this root 6 maybe get cancelled. What I am getting now? 100 minus 4 by, let's say, plus 4 by root 6, 2 by root 6, and minus 2 by root 6. Is that fine? And what will be then be? 1 minus 4 by root 6.
How the second line came? Minus 2 by root 6 and minus 1 by root 6?
You have just multiplied minus 2 inside, right?
Previous
I
one.
think the square roots
This
will
one?
get
Yeah. This one. How this came?
It is
My
minus.
Z1, right?
Z1 transpose E1.
Hmm.
This is Z1
No,
transpose
no,
E1, na?
Z1 okay.
Okay, this is Z1. Okay,
Okay.
this is
See, what
Z1.
is what is this? This
It
part?
is minus 2 by root 6.
Minus 2 by
Yeah,
root.
so
This
it
is
will be
Z1.
1 by
Okay,
3
so yeah,
minus 1 by
is how, what was the value? Minus 2 by root 6. So basically, this entire thing will become
Confusing. Confusing.
1 by 3 minus 1
minus
by
2 by
3.
6. So minus 1 by 3, right?
Hmm.
Okay, okay. So let's see. What is this
Please
part?
do again, sir.
No, no,
How
this
this
is
minus?
this is Z1 transpose E1.
Yeah,
Huh?
this is Z1 minus 2 by root 6
This is Z1
minus 1 by, yeah,
E1. What is the value?
yeah,
Minus
minus
2
2
by
by
root
root
6.
6.
Okay.
Yes, yes.
What is the value of uh, norm of Z1?
Root 6.
So Z1 was what? Z1 was basically minus 2, minus 1, and 1, right?
Yes.
Okay.
So
It is
norm of
root 6.
Z1 is equal to
Root
root of
6.
4 plus 1 plus 1, which is root 6. Is that fine?
Mm-hmm.
So this vector, basically we wanted to find out this part, right? This portion. This portion is this, so which is minus
Got it. Minus 1 by 3.
by
Correct.
root 6.
Root 6 into
Root
root 6 is 6 1 by 3. Correct.
6
It will
and
be
then
norm square, right? Because you transpose
yeah,
Z1
norm square,
transpose Z1.
norm square, right?
So 6,
So no. Basically, when I square or
because it is Z1 transpose
transpose
Z1, so
Z1,
it will be norm square.
so it should be equal to yeah, correct. So it will be
Norm
norm.
of Z1 square.
Norm of Z1 square. Yes.
Then you will not have that 1 minus 1 by root 3. It will be uh,
6 root 6. 1 by 3 root 6.
will
Yes.
that it should be equal to
1 by 3 root
so
6.
Z1 transpose E1 upon norm of Z1 square is equal to minus 2 by root 6 into 6. Basically, it is minus 1 by 3 root 6. Is that fine?
Yes.
Yeah. Is that correct?
Yes.
So this part will be
And multiplied by Z1.
minus 1 by no. This Z1 is separate. So it is like 3 root 6. Is that fine now? Now is it okay?
Yeah.
Yes.
So what the final answer will be is equal to 100 minus. So if I do the multiplication, so this minus sign I'm
1 by
looking at is
18.
uh, 1 by 18. Okay. 1
We
by
are taking Z1 as a
No,
unitary Z1, or we are taking original Z1 minus 2
2
to
by
1.
1 by 9.
what happened? This is okay,
This
right? No,
Z1,
Yeah,
Z1.
correct.
What
Z1
is
you can
Z1?
you'll have to take this one only, right? The unit vector. If you don't also take, it's fine. See that root 6 is anyway that it's constant, right? Which is multiplied. It's the same vector, right?
Yeah.
So it doesn't.
But
It will not
whether
affect
we
much.
should take
You
unit
need
vector.
to see whenever you do this all of these calculations, right? It's better to calculate with respect to unit vectors, right?
Okay.
Because it will make your basis like because last again at the end you will have to do the same thing. Fine. Okay, I'll not waste much time here
Okay.
because then
Minus 1 by 18.
how much it is? Minus 1 by 18.
Minus 1 by
So
18.
if you just do the calculation, what I'll get is minus 8 by 9, right?
Yes.
Minus 9, oh, sorry, minus or plus? Plus, right? Plus 8 by 9,
Plus
minus
minus 1 by 8
8,
and 1 by
18,
8.
18.
1 by 18
And 1 by
and 1 by
18.
18.
So still you can actually take the some values common. So I'll get what is it? 8 minus 1 by 2 and
2. 1 by
by
2.
2. So it's 9. What else I can do? So I'll have to make this also as a unit vector, right? So if you just do some calculations. What? Okay, maybe you'll have to divide it by its length. So I think maybe okay, I'll do it for one. Then we'll see. What is the length of it? 64.
64.5.
4 is 1 by 4. So what can we do? So maybe I'll do one thing. I'll just make twice, right? So it is like 16 minus 1 and 1. Is that fine?
Yes, yes, yes.
So we
18.
get some constant. So it will be root of 18. No, right?
258.
256 plus 2, right? 258, root of
258.
258. And then you will again have to disintegrate all of this, right? Like,
16 point something.
no, no. That is correct. I understand that part. What we can do in terms of like 3 times something or something in the case of like roots or something, right? You understand my point or no? If I just 3
It's coming
into,
is 2 root 64.5.
so 3 times, can I say 3 times
No, it's not a multiple of 3.
uh, 13 plus 2? It should be right. The
Yes.
sum is 15, so it should be multiple of 3, right? So
Yeah, yeah. It is multiple of 3.
258 by 3,
It comes
right?
86.
686.
3
So
into 86. 3 into
okay. So
86.
then again, it is not of any use for us, right?
Yeah, because we want 9 actually.
Huh? Yeah, we'll need one square. So can we get any sum?
We get 4, so it's 2 root 64.5.
Okay, just a minute. You do the calculation. I will just come back on that. So you should get these values. So 1 by root 3 minus 1 by root 3 and 1 by root 3. So just check whether you are getting those values or not. I'll just come back into nets. Okay, are you able to do that? I don't know. Some calculations are not like they are too much, right? Maybe, but it's okay. What I'm saying is, uh, let us say, okay, I'll not do the calculation right now. Maybe after some time we'll do that. Let's order 10. So let us say you got this, but you understand the idea, right? How to do that? So how to use this Smith procedure? So now we are done it for one vector. We'll have to do it for another one. Okay, is that fine? Hello, am I audible?
Yes, sir.
Yes, sir, or devil, sir.
Okay, it's fine. So I'll not do the calculation right now. Maybe it will take a lot of time again for us. But basically, you will have to find out this vector. You use that procedure, right? You just have to, if these two vectors are not orthogonal to each other, you will have to take a projection, and the error vector and its projection are orthogonal to each other, right? Maybe after 10-15 minutes I'll do the calculations, but we'll try to find out the procedure first, right? So let's say you got this matrix, u1 matrix, fine. Okay, what is the next step? if I just do the multiplication, so you will this, let's say this is a unitary matrix. You take its conjugate and you get you multiply that with A, and you get this part. Fine. Why it is written U1 transpose here? Because we are not dealing with the complex values, right? So a conjugate of transpose in real case, it is equal to transpose only. Fine. It's fine.
Yes, sir.
Okay, so now let us say this is the vector, and as per our procedure we have seen earlier, the first value is equal to lambda 1, right? So our lambda 1 in this question was equal to 1. So you actually will get 1 here. If it is some other lambda 1, you will get that lambda 1 here, and these two values will become 0, and you will get some values here. And this is a matrix now, minus 3 minus 3 0 root 6 minus 3. Consider this matrix as B. Find out its eigenvalues. So the eigenvalue of B is coming out to be, let's say, minus 3, because both of these eigenvalues are minus 3, right? Why?
Yeah.
Yeah, it's upper triangular matrix. So okay, so and E2 is 0 1. So E2 is basically the eigenvector corresponding to this minus 3, and for 2 cross 2 matrix. So you can see that the dimensions of this vector is, it's two-dimensional vector, right? The initial vectors we have found out, the eigenvectors, they were three-dimensional, right? No, you understand the difference between this? What you have to do
Yes.
now? Yeah, now we have to find out its eigenbasis again. So 0 1, we have to find out its orthonormal basis. So what is orthonormal basis? So you already got like 0 1 eigenvector. So let's say 1 0 will definitely will be a orthogonal eigenvector corresponding to it, and you make the unitary matrix by combining these two vectors, that is 0 1 1 0. What is B here? This one is the B, right? So you found out it's B star BP, and that is this vector. This matrix will come out like minus 3 root 6 0 minus 3. And then what you have to do? What was okay? So you have to find, so this matrix B, right? B is in, what is the dimensions of B?
2 by 2.
2 cross 2 matrix, right? Yeah, 2 by 2. So that means if I do this P transpose B P calculation, the output is 2 by 2 matrix, but you need a 3 cross 3 matrix or 3 by 3 matrix, right? Because your initial matrix was of 3 cross 3. You have to find out U2 star such that I can multiply that, or I have to find out U2 such that I can, if I multiply that with U, that this equation, U1 star A U1, I should get the upper triangular matrix. So U2 will be defined such that this U2 is equals to, so the first row will be 1 0 0 1, or maybe first column you will have to find out like this by doing this zero zeros here, and keep this P matrix, which is 0 1 1 0, the orthonormal basis, right? We'll keep it here, and now uh, do the multiplication. Like you find out its transpose and multiply with this part. So initial matrix, what we have found out is this one, right? 1 minus root minus 8 root 2 minus 12 root 3. This matrix I have multiplied with u2 star on the u2 star, that u1 star a u1 into u2. If I do that calculation, whatever matrix I'm getting, it's a upper triangular matrix. I'll solve that. I'll solve that. Don't worry about that. But I hope this procedure is fine for you. I will finally I'll tell about you the spectral theorem, and then we'll solve that problem again. Okay, if we have done some mistake, we'll try to see that. Fine. What is spectral theorem says? If a matrix is Hermitian, then what happens is it is unitarily diagonalizable. What does that mean? You will find a unitary matrix such that if I multiply that with matrix A, I will get a diagonal matrix with real numbers. Okay, so same procedure we have to use, like which we have used for in the Schur's theorem. We use that, and then we'll get that diagonal matrix here. We'll see that part. Now I will show the previous problem, right? Okay. So Z1 was equal to minus 2 minus 2 minus 1 1, right? Minus 1, and we said that E1 equals to 1 0 0 and E2 equals to let us say 0 1 0. Fine. What was the next step? We said we'll find it out we'll find it out the uh, vectors by which are orthonormal to each other by Schmidt's process, right? So let us do one thing. Instead of doing that, or instead of finding out the Q1 part initially itself, we'll do it later. So what I'll do is, maybe I'll just say that it is equal to E1 minus. So what we are going to do here? We are going to project E1 onto
Z1.
Z1, right? So the error vector will be what?
E1 minus Z1.
So B was equal to E1 minus
Z1.
not Z1. It will be
Okay, no.
it will
E1
be
onto Z1.
Z1 transpose E1 upon Z1 transpose Z1 times Z1, right? Okay, is that fine? We'll do that. Minus, what is Z1 transpose E1? This value is minus 2, right?
Hmm.
And what is the length of Z1? It's root 6. Fine. Here it is minus 2, minus 1 and 1. Okay. This part is fine.
Yeah.
So here 1 0 0 minus what is the value here then? Plus 4 by root 6, then 2 by root 6 and
1
minus
minus
2
2
by.
by 6.
Is that fine? What I
Yeah.
have done here, what was the previous difference between the previous calculations and this one is, I didn't take the norm of Z1 in the initial stage itself, right? They're doing it in the later stage. That is also fine. So if I try to use that, what is the calculations here, or what are the calculations here? Okay, basically it's like 1 minus 4 by root 6, right? So basically this will become root 6 minus 4 by root 6, right? Minus 2 by root 6 and
Minus 2 by
plus 2 by root 6.
Plus 2 by root 6.
So that is my B. Okay, and what is the first orthonormal vector, or first vector in this orthonormal basis is Z1's thing, right? So it's minus 2 by root 6, minus 1 by root 6 and 1 by root 6 is separate. What about this vector? This vector is what is the length of this one? Can you tell now what is the square of uh, this part? Root 6 minus 4 square by 6, right? This first quantity. Can I say that it is A minus B square?
Yes.
What is the A minus B square?
6 minus 6 plus 16 minus 8 root 6.
Okay, 6 plus
16 minus
8
root 6
by
6.
6. Okay. Right. So that means, can I say that it is 22 minus something? 22 minus 8 by root 6. Can I
Yeah.
say that for entire thing, for entire this, the 6 is the denominator, right? So I'll say that 22 minus 8 root 6.
Yeah.
Remove it, but I'm just saying that it's length square, but we wanted only length. Yeah. So it will be square root. So everything will be under square root
Hmm.
and divided by its 6. Okay. What is the next part? Plus 4 plus 4. Right. So like plus 4 plus 4. So basically, this will become what? Uh, 30. Right. 30 minus 8 root 6 by 6. So it's like it's kind of right like this. Oh, still it's like getting weird equation, right? So how to solve this part is I don't know, but how Sir has got like root 3 here? Okay, and I don't know some calculations. Are we not doing any calculation mistakes here? Am I audible?
Yes, sir.
Audible, sir.
I think my screen has struck or what? I'm not in. Okay, I'm able to change tab now. Okay, what I'm saying is whether what is the problem here? I don't understand. We are doing this correct procedure, right? If I'm just multiply this with okay, okay. Have you if anyone has solved it this problem? Tried it already? I don't know. Some calculation mistake. Either I am doing it or maybe this is the because the procedure what we are doing right that is correct only. Just do it one more time.
Should we check this Z1, transfer Z1? In?
Okay, we'll do that maybe once again if I'm. This page is not responding, right? Not able to. Okay. Fine. Okay. Can you just can somebody will do that? Okay. Please do it like independently so that if I'm doing it again, so let me Z1 transpose Z1, right? Or anyway, these are not the complex numbers, so it is -2 -1 1. Or I don't know whether this vector was correct. Shall we check that first? If this is the correct eigenvector that
Yeah,
is
yeah. Please check, sir. The iron vector check.
if let's say if we
Yeah,
I
maybe they get a vector.
yeah 5 8 16 and 509 and there's a -3 -5 10 3 -5 and -10. Okay, so yeah, so now it will be 5 minus lambda, right? 8 16 5 minus lambda 9 minus 3 minus 5 minus 10 minus lambda, right?
Yes, yes.
Okay, so the next thing is I'll have to uh, find its determinant, right, and equate it to 0. Okay, So it will be 5 minus lambda into minus lambda times minus 10 minus lambda plus 45, right? Plus 45 minus 8 into 5 times minus 10 minus lambda plus 27, okay, and plus 16 into 25 minus 25 minus 3 lambda, right?
Correct. Correct.
And that is equal to 0. Okay, so here 5 minus lambda into that equation will be 10 lambda plus lambda square plus 45 minus 8 into minus 50 minus 5 lambda plus 27
So,
plus 16 into 25 minus 3 lambda equal to 0, right? Next will be 50 lambda plus 5 lambda square plus 5 and 45 into 5, like 225, right? 225 or 205. 225 is correct. Minus 10 lambda square minus lambda cube minus 45 lambda plus 400 plus 40 lambda minus 216, right? 216. Check the calculations, huh? And minus 25 into 16.
So 400.
350. Huh?
Sorry.
How much? 400, right? Correct. 400, right? So that will be minus 400.
minus 48 lambda.
And minus 48 lambda equal to 0. Okay.
Cubic equation, how to solve?
That will do that. That's not a problem. The problem is these are very big numbers, right? So okay. Minus lambda cube. See, solving in front of the screen, right? It will be sometimes it is tough. If I solve it like myself,
Yeah.
sometimes it will be like easier.
Yeah, you are correct.
So minus lambda cube, 5 lambda square minus 10 lambda square, and okay, so that is 2 lambda square terms. So that is equals to how much?
Minus 5 lambda square.
Minus
5
5 lambda square.
And then we'll see the lambda terms. So
55 lambda
minus 45 lambda, 40 lambda, and minus 48.
minus 3 lambda.
Correct? Okay. I'm just 90 minus 93. Yeah, correct. So it is minus 3 lambda and
16 minus 400 minus 2
225
minus 4
minus 400 and plus 400. So minus 400 plus 400, it will get cancelled.
Plus 9.
225 and yeah, plus 9. Plus 9 equal to 0. So I can make it positive. Lambda cube plus 5 lambda square plus 3 lambda minus 9 equal to 0, right? Okay. So we'll have to find out what is its like first root. So first root, if I'll put it 1, right? Let's say lambda equals to 1. So it will be 1 plus 5, 6, 6 plus 9, and 9 minus 9, 0. So lambda equals to 1 is its root, correct? Is that correct?
That way we have to find out a lambda
No,
minus
that is
1.
yeah, first root. So let us say lambda equals to 1. What is next step? So let's say lambda minus 1 is the root.
Factor of that.
Right. So we have to find out the next factors, right? So how to find it out?
Divide by lambda minus 1.
Yeah. So there is this procedure.
Such type of question will come in the examination.
No, it will take exam and all, it will take, see how much time we are here solving, right? So 15-20 minutes, one, it will not be that tough. If it comes also, it will be like maybe theoretical one, or maybe 2 cross 2 matrix, right? 3 cross 3 will be like tougher. But okay,
Okay.
I'll show you anyway how to solve it, so that
Yeah, yeah,
will
yeah,
tell you better.
yeah.
So we are saying that one is its solution. What are the coefficients? 1, 5, 3, and -9. So 1, I will keep it as it is. So 5 minus 1, 4. Here it is 4. 3 minus 4 is, this is 1 is the solution, right? If I put 1 plus 5 plus 3. That is correct. So
Which method is this?
you can find it out, like this was there, right? You don't use that method previously.
No.
We just do the divide the whole expression by lambda minus
and
1.
and, and how will you solve it? Actually, see, what you should get 0 here, and whatever the coefficients you are having right here, let's say whatever coefficients you are having,
Okay.
we'll make that
Yeah.
a quadratic equation, and that quadratic equation you will have to solve like how you regularly solve it. So that
Mhm.
is the procedure. So basically, uh, okay. So I think I, one is the right one should be. Okay, I think it will here we'll get 6, 6 and 3 9, right? And then you'll get 9, 9 plus 9 0. So you'll get this part. Okay, if you don't know, you can search it later. So first is this one, right? Lambda minus 1, and this will be your quadratic equation will be lambda square plus 6 lambda is 9 equal to 0. And then you can find out its so what are the roots? Lambda minus 1. Here it is lambda plus 3, lambda plus 3, right? Equal to 0. What I have done here, maybe I'll tell you in a brief what we have done
Yeah, yeah.
here. What are this part? These are this 1, 5, 3, and -9. They are the coefficients of this, right? This 1, 5, 3, and -9. We already said that lambda is the, okay, lambda equals to 1, right? Actually, lambda equals to 1 was my root, right? First root, how you found out? You just substitute that one and see that whether if it is
Yeah.
equal to 0. If let us say this time, let's say we have substituted one and we have got 0, right? If not, then what you do, then you just go for
Minus
minus
1.
1. And then if you don't get the answer there, then what you do next? Go for plus 2 and then minus 2, like that.
Yeah, yeah.
Okay.
Trial and error method, first
uh,
find the root.
for first root, and then what you do is you find out like this is the method where you can. So what I done is, like, I have kept 1 here as it is. 1 into 1 is 1, so 5 into 5 plus 1 is 6, 6 into 1 is 6, and 6 plus 3 is 9. And you, so this remainder 0, right, we'll have to ignore, and whatever these coefficients are there, you just take them as like you just so you can't take that now, like lambda equals to 3, so that degree 3 will remove, and this coefficient will become the coefficients of your 1 degree less. So
Yeah, how
that is
this 169 came? How this 169 came?
so 1 is basically here, 1 was there, I just kept as 1 here. 1 was
Okay,
the root,
okay.
so multiply 1 with 1, I get 1 here. So 5 plus 1 is 6, 6 into 1 is 6, and 3 plus 6 9. Okay, that is, this is also like very popular method, you can just check it later, but that is okay. So here if you'll say that lambda equals to 1 minus 1, or sorry, plus 1, minus 3, and minus 3, right? And now we have taken lambda equals to 1. So what are the so later, if I do it here, it's fine, right? What is the 5 minus 1 is 4, 8, 16, 5 minus 1, 9, minus 3, minus 5, and minus 11, right? This is the matrix. Okay.
What?
What I have done here, for lambda equals to 1, we have to find out its eigenvector, right?
Lambda was 1, na, first.
So for lambda equals to 1, what I have done is I have just substituted 1 here, right, instead of lambda.
Yeah.
And to get that a minus lambda I equation, right?
Yes.
Okay, so this is my matrix now. And what will be, which equation we are solving then? x1, x2,
x3
x3 equal to,
0 0.
this is a minus lambda I to x equal to 0, and for we are doing it for lambda equals to 1. Okay, so
Yes.
what is the next step? You just make it a Gaussian elimination method, right? You can use that. So I'll just make the first row 1. So first element as 1. So it will be 1, 2,
4.
Yeah.
4. Then here the next step will be making it 0. So what, how it will be? It's like R2 changes to R2 minus 5 times R1, right? With the new row, right? New first row. So this is 5. So the second one will be what? Minus 1
Minus 14.
minus 10.
Oh shit.
Correct,
Yes.
na?
Yes.
And the third element will be 9 minus 5 times 4. So that is 20, right? So that is minus 11 again. Done.
Yes.
And the third row is minus 3 minus 5 minus 11. What I'm doing here is, again, I'll make the second row as like, because we need
1.
this to be pivot, right? So that will be 1 2 4
0 minus
0
1
1.
minus.
I'll
Yeah,
keep it
1.
1. That is okay, right?
1,
So
1.
minus.
Okay.
Oh, okay, but I think we have to. Okay, sorry, we missed one more step, right? We'll have to make R3 also 0, right?
Yeah.
So R3 changes to what?
R3
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 plus
plus
3
R2.
R1 plus 3
3R1
R1.
plus 3R1.
Correct, na?
Yeah, correct.
Here 1 2 4 0 minus 11 minus 11. Here it will be 0. So now minus 5
Plus
plus
6.
1,
6.
1,
1,
1.
and
1,
then minus 11 plus 12 is 1.
1.
Okay,
Now it is okay.
now then I'll make this as pivot, and I wanted it to make it to be 1. It is 1 2 4 0
1,
1
1.
0 0 0. Then,
Yeah.
right? Correct? Why this
Correct.
0
Correct.
0? Because
Correct.
and is equals to what? X1 x2 x3 equal to 0 0 0. So there were no changes in the right hand side, right? Because all the elements were 0. So we'll have to solve this equation. So what is the equation then? X2 plus x3 equal to 0. This is equation 2 or 1 possibly, right? So okay, that gives me what? X2 equal to minus x3. Fine.
Yes.
And then x1 plus 2x2 plus 4x3 equal to 0. So x2 is equals to, it's minus x3, then x1 minus 2x3 plus 4x3 equal to 0 by substituting this value here, right?
Yeah.
And that gives me x1 uh, plus
Plus 2x3.
2x3 equal to 0, which gives me x1 equal to minus 2x3. So that means what will be my vector? If I have x3 equal to 1, it
Yes.
will be minus 1 and it is minus 2. So that means it's a correct eigenvector, right?
Okay.
Right. So minus 2 minus 1 is plus 1 is correct eigenvector. Is that correct?
Yes.
Okay. So that is okay. Then we find out, like, okay, then I think this took a lot of time again solving this. Okay, so what you can do is, maybe now I'll stop here. Can you just find, like, take these three vectors? So that means this is the correct one. I have done some mistake maybe somewhere in the calculations. Can you try this one to use the Schmidt procedure? Schmidt procedure also I told you already. So you try this one. You understood this process, right? The Schur's theorem, how to do that. What you will do here?
Yeah, we'll try it, sir.
Yeah,
In the
you
next-
try it, but can you tell me one more time? What, like, we'll summarize it last time. So, what is the procedure after this? You found out the first eigenvector, then
We will find Z1 and put in that.
uh, then we wanted to find out the orthonormal basis, right? That will be my
Orthonormal.
that will be my one unitary vector one. Let's say u1. Okay, what you do next? You multiply this u1 with a, right? So and how in which way? u1 star a u1, right?
You won't transpose A because it is a
So
not
real
not
matrix.
real matrix.
So u1 transpose a1, au1, you will get this matrix. Uh, in that, this b, consider this b. Then what do you do then? You find out its eigenvalue for b
Again, for this B, we have to find the eigenvalues.
and its
Again,
eigenbasis,
eigenvectors.
and then orthonormal basis for those, right?
Mm.
Consider this matrix as p, that which is got from, like, we just got it from orthonormal basis, and that actually, if I multiply this, that p star bp, I'll get this this part, right? Minus 3 root 6 0 minus 3. You wanted that, so that you make this u2 as 1 0 0 0 0, and this p is what? This one, 0 1 1 0. And then this multiply this, use this u2 to multiply this u1 star au1. That is okay. Or shall I show you how to do it? Like, maybe if I take these values as, I will not again solve it, because we have solved it 2 times. I did wrong it, right? But I'll just, let's say I'll take those values and try to find it out. Okay. What is u1? Let us say u1 is your orthonormal basis. We have found out it's what, root 2 by root, so minus root 2 by root 6, minus 1 by root 6, and 1 by root 6. What was the values? 1 by root 3 minus 1 by root 3, 1 by root 3, and 0, 1 by root 2, and 1 by root 2, right? Okay. Let's say this was your u1. What you do next is you take its transpose. And what was its transpose? Minus 2 by root 6, minus 1 by root 6, 1 by root 6, 1 by root 3, minus 1 by root 3, and 1 by root 3, 1 by root 6, sorry, will be 0, 1 by root 2, and 1 by root 2. What is A matrix? Can you tell me what is A matrix? 5. 5.
We don't remember it.
Yeah, okay. I'm having just a minute. 5, 8, 16. 16. 5, 0, 9, and minus 3, minus 5, 10, or minus 10, and into u1, which is this matrix. Okay. So if you do this calculation, right, will you do that, or okay, maybe I'll do for one case. What will be the calculations? You see, it's like a very huge calculation, right? So, but
Minus 10 by root 6
minus 10 by
plus
root 6.
plus
Uh,
5 by root 3.
uh, so okay, you can do it later. Still.
Yeah, we can do it.
So first value, is it coming 1? Let us see. So minus 10, minus 5 plus 3, right? So
Not coming.
minus 10, what is it? Minus 5, and no, it is not like this, right? It is like, it's just the calculation of this part, right?
Yeah, after that you have to multiply with the U1 also. No?
Okay, then you will get
It will
like,
take time, we will do that.
okay, so this is 1 8 root 2
Sir, we
minus.
will try. We will try it. You
Huh.
just do it and share in the discourse. We will see that also.
Fine, fine. So okay,
It is better how to. We will compare
yeah,
there.
okay. So, but you
If
understand the procedure, right? How to
yeah, yeah.
do this? That is important.
Yeah, we got the procedure.
And what is
But
spectral
we have
theorem?
to do. We have to do it again.
You will have to solve it. Like it will take
We
time
are
for
not.
you
Yeah,
also.
yeah.
Yeah,
We are
yeah,
not confident, so
yeah.
we have to
Yeah,
do it.
you just check it. If it is not, then we'll discuss in the next
Yeah,
session. Right?
yeah.
Okay, what is the spectral theorem now? Spectral theorem says that if a matrix is Hermitian, then it will be unitarily diagonalizable. Fine. So that means you will find a such a U, or use such matrix U, that if you have its, like if it is unitary matrix, right, then it should be U star AU will be equal to a diagonal matrix. So it is, this is the proof using the Schur's theorem, that these two upper triangular and lower triangular, they actually become diagonal, right? So you can see that later. But how to solve this is, let's say, okay.
Not right now. I think that first we have to do previous one.
Okay, do it. Then maybe next session. Okay, Shubham will take that time. He might will discuss with you. You just go through these slides also. This is once you understand Schur's theorem, right? Understanding spectral theorem will be easier again, right? If not, then maybe we can discuss in the next sessions, next to next, like after the revision
Yeah,
session.
after the revision session, we will do it after the quiz also because
Yeah, after quiz. Okay.
up to week 4 only we have to revise it, no?
Sure, sure. Yeah. Okay then. I'll stop here. Okay, so let's
But
meet
graded
in the next.
assignments are there now. For week 5, graded assignments are also there.
Yeah, yeah, yeah. So grade assignment is not